Hello friends, it's a beautiful morning here and I hope everyone is doing well. I know right now you are preparing for your mocks which are maybe coming very soon. And I know these videos might be helpful and might be helping you to practice physics as you prepare for your mocks. Today I want you to take you back to force, density and pressure. And this is going to be episode 2 of force, density and pressure. This is part 2. And do not forget within these videos, I said for force, density and pressure, we should expect questions or we should expect to discuss questions about density as a unit or density in general, pressure. We shall talk about upthrust, Archimedes principle many times, moments or torque, equilibrium of forces. By the way, when I talk about moments or torque, it means we do not forget a couple, which is two forces acting in opposite directions whose line of actions would never meet. So equilibrium of forces, center of gravity, and a lot more. And without wasting time, I would like to take you just to the past paper question documents so that we start solving them from where we stopped in part 1. So I hope in part 1 we stopped at in part 1 I think we stopped around there, and I just want us to begin from where we stopped in part 1. So we stopped around there. So let's start with this question here in part 2. A rigid plank is used to make a ramp between two different horizontal levels of ground as shown in the figure here. Point A at one end of the plank rests on the lower level of the ground. The force acts on and is perpendicular to the plank at point B. So the force at point B is perpendicular to the plank. That means the perpendicular distance of 45 newtons from A is going to be the sum of 1.1 plus 0.3 plus 1.5. The plank is held in equilibrium. That means the resultant moment and the resultant force is 0 by a rope that connects point D on the plank to the ground. The plank has a weight that may be considered to act from its center of gravity. So C is at the center. C is at the center of gravity. The rope is perpendicular to the plank and has tension T. The plank is at an angle of 38 degrees to the vertical. The forces and the distances along the plank of points A, B, C, and D are shown in the figure. Show that the component of the weight that is perpendicular to the plank is 59. So we look at the weight. The weight is given as 96. The weight is given as 96. Now we want a component that is perpendicular. So I will draw a perpendicular line to the plank. So we are going to resolve the 96 newtons perpendicular to the plank. We can use 38 degrees or we can use this angle here, which is going to be 52 degrees, because we are looking for a component which is perpendicular. So it means the sum of the 38 plus the angle between the force and the vertical and the perpendicular should be 90. So when I use 52 degrees, this component of course is going to be 96 cos, 96 cos 52 when I use 52 degrees. When I use 32 degrees, the same component will be 96 sine of 38. So the component they want, the component is going to be equal to 96 sine 38 degrees or 96 cos 52 degrees. So we can verify with the calculator whether it is going to give us that. So 96 sine 38, it is 59.1, which is approximately 59. You can even check the second one, 96 cos of 52. It's the same thing. So that is the component. By taking moments about end A of the Planck, calculate the tension T. So we are going to take moments about end A to be able to find the tension T. So first of all, since we have already got the perpendicular the component of the weight perpendicular to the Planck, so we shall be using that component in taking moments. And if I change the color here to see which moments, which forces cause clockwise moments and anti-clockwise moments. So we have, because I want to use the distance, perpendicular distance as 1.5, so I will just take the component of the weight perpendicular to the Planck. So the component of the weight is going to cause an anticlockwise moment about point M. The tension is also causing an anticlockwise moment about point M, but the 45 newtons is causing a clockwise moment about point A. So remember, moment is the product of force and perpendicular distance from the fixed point that we are taking moments about. So to take moments, for the anticlockwise moments, if I start with anticlockwise moments, I have the tension T times its perpendicular distance, which will be 0.3 plus 1.5. That is the perpendicular distance of T from A. Plus, for the tension, we have the component, which is 59. We shall just use 59. The component of the weight of the Planck, 59, times its perpendicular distance from A, which is 1.5. Since I'm using the component, I don't need again to look for the perpendicular distance. If I use 96, I will have to look for the perpendicular distance. But since I'm using a component which is at 90 degrees to the Planck, then this is going to be, its perpendicular distance is 1.5. So this is the sum of the anticlockwise moments, and they should be equal to the sum of clockwise moments, which will be 45 times the perpendicular distance, which is going to be 1.1 plus 0.3 plus 1.5. So that is, those are going to be the moments. So I'll just take this to where we are supposed to solve this from, and we obtain our solution. So they said by taking moments about end A of the Planck, calculate the tension T. So we have seen the moments. We have seen that the sum of clockwise moments was T times the perpendicular distance, which is 1.5 plus 0.3 plus the vertical component, or I mean the perpendicular component of the weight, which was 59, times its perpendicular distance, which is 1.5. This was equal to the sum of the other moment, which is 45 times 2. I think that is 2.9. This is 1.1, that is 1.4, that is 2.9. So this is times 2.9. So we can verify to find the answer. I'll start with the right hand side, 45 times 2.9 minus, I take this one to the left, to the right hand side, minus 59 times 1.5. Then we are going to divide by, because I'm making T the subject, so we are going to divide by 1.5 plus 0.3, which is 1.8. So divide by 1.8. So that gives us 23.3 recurring. So that is 23.3, or approximately 23. So that will be the moment. State what is meant by the center of gravity of a body. The center of gravity is the point where all the weight, the entire weight of the body is always considered to act or seems to act or is taken to act. The point where all the weight of the body may be considered to act. May be considered to act or seems to act. That is what we call center of gravity. There is a point, whether on the body or not on the body, where all its weight may be considered to act. That is what we call the center of gravity. A uniform wooden post AB of weight 45 newtons stands in equilibrium on a hardy ground as shown here. We can look at the diagram. Okay, so end A of the vertical post is supported by the ground. A horizontal wire with tension T is attached to end B of the post. Another wire attached to the post at point C is at an angle of 60 degrees, as we can see, to the horizontal, and has a tension of 38 newtons. The distance along the post of points A, B, and C are shown there. Calculate the horizontal component of the force exerted on the post by the wire connected to point C. So this is the wire connected to point C. We want the horizontal component. That means we are going to resolve 38 newtons to the horizontal. To the horizontal, this is adjacent, and the 38 newtons is in the opposite. So if you are still not very comfortable with resolving, if I draw a perpendicular triangle here and I use the horizontal as adjacent, that would be cos. Cos of 60 is equal to the adjacent divided by the hypotenuse, meaning that the adjacent is going to be 38 cos of 60. So the horizontal component, which I will call f in the x, is going to be equal to 38 cos of 60. Or if you're good at resolving, you can just use this angle here, which is 52. But using 52 to the horizontal, that would be 38 sine. No, that is 30, not 52. That is 30. If you use that angle, it will be 38 sine of 30. Of course, the sine of 30 is the same as the cos of 60. So you can check the horizontal component, 38 cos of 60, which is 19. So the horizontal component of 38 newtons is 19 newtons. By considering moments about end A, determine the tension T. We are going to take moments about this point A. So we first of all have to identify which forces cause clockwise and which ones cause anti-clockwise moments. So let's identify them. So the force of 45 newtons is acting through point A. Its line of action is through point A, so this one has no moment about A. That's number one. No moment about A. The tension, the vertical component, the horizontal component of the tension, we have already found it. It is in that direction. The tension, 38 newtons, has a moment. But instead of using the 38 newtons, we shall use its horizontal component, which is 19 newtons, because its perpendicular distance is easy to find. And the perpendicular distance will be this one here, which is 0.9 meters. And this one is causing a moment which is in that direction, and that is clockwise. Then T is causing a moment which is in this direction about A, which is anti-clockwise, and its perpendicular distance is 0.9 plus 0.3. Therefore, taking moments about a t times its perpendicular distance, which is 0.9 plus 0.3, that is perpendicular distance from A, should be equal to the horizontal component of 38 newtons, which is 19, times the perpendicular distance, which is 0.9. That gives us the clockwise moment. The sum of anticlockwise moments should be equal to the sum of clockwise moments for equilibrium. Therefore, we are going to equate those two moments. So we shall say t times the perpendicular distance, 0.9 plus 0.3, which is 1.2, should be equal to 19 times the perpendicular distance, which is 0.9. So from the calculator, we have 19 times 0.9 divided by 1.2, and this gives us 14.25. So T is 14.25, which is approximately 14 newtons. Calculate the vertical component of the force exerted on the post at end A. Vertical component. So first of all, the 38 newtons has a vertical component which is downwards. So when we resolve 38 downwards, it will have a vertical component downwards, which is going to be given by, if the vertical component is 38 cos 60, then that is the horizontal component is 38 cos 60, then the vertical component will be 38 sin 60, and that will be downwards. And there's a force of 45 newtons acting downwards. Since the resultant force in any one direction should be equal to 0, it means the force exerted at point A should be equal to 45 newtons downwards plus 38 sine of 60. That will be equal to the force, the vertical component of the force exerted on the post at end A. So this will be 45 times 38 sine of 60. So I said 45 plus 38 sine 60, which is 77.9. So the force there is, the vertical component of the force there is 77.9, which is approximately 78 newtons. A spherical oil drop has a radius 1.2 times 10 power negative 6. The density of the oil is 940. Show that the mass of the oil drop is 6.8 times 10 power negative 15. We want mass. And we know that density is mass over volume, meaning that the mass is equal to the density times volume. Where the density is going to be, where the volume, because it's spherical, the volume of a sphere is 4/3 pi r cubed. So it means the mass is going to be the density, which is 940, times the volume, which is 4/3 pi, and the radius is 1.2 times 10 power negative 6, and this is raised to power 3. So 940 times, I'll just say times 4 pi, then times, open brackets, 1.2 exponent negative 6, and this is raised to power 3, divide by 3. So that is 6.8 times 10 power negative 15. So this is 6.8 times 10 power negative 15. So that is the mass of the oil drop. The oil drop is charged. Explain why it is impossible for the magnitude of the charge to be 8.0 times 10 power negative 20. Of course, we saw this in one of the units, maybe in electricity we mentioned this, but this is actually in electric fields. Explain why it is impossible for the magnitude of the charge to be 8.0 times 10 power negative 20 coulombs. 8.0 is the same as 0.8 times 10 power negative 19 coulombs, which is a half of 1.6 times 10 power negative 19 coulombs. And we know that 1.6 times 10 power negative 19 coulombs is the minimum charge. So it is not possible for the charge to be 8.0 times 10 power negative 20 coulombs. So you can say the minimum charge or the smallest charge or the elementary charge on a drop is 1.6 times 10 power negative 19 coulombs. So it is impossible to have such a charge according to Millikan's experiment that we saw in A level. State what is meant by center of gravity again. We shall define this many times until we are very confident with it. The center of gravity is the point where all the weight, the entire weight, all the weight of the object, all the weight of the object may be considered all the weight of the object may be considered to act. It may not be acting there, but it is considered to be acting there. That is what we call the center of gravity. All the weight of the object is considered to act at that point. That is the center of the gravity. The word all is very important, and considered to act is very important. A uniform square sign with sides of length 0.680 meters is fixed at its corner points A and B to the wall. The sign is also supported by a wire CD as shown here. So let's look at the sign. So the sign has a weight W and a center of gravity E. The sign is held in a vertical plane with sides BC horizontal. Side BC is horizontal. The wire is at an angle of 35 degrees to side BC. As we can see, the tension in the wire is 54 newtons, as we can see. The force exerted on the sign at B is only in the vertical direction. The force exerted on the sign at B is only in the vertical direction. Okay. The force exerted on the sign at B is only in the vertical direction. Calculate the vertical component of the tension in the wire. So we find 54 newtons in the vertical. That is now very easy. When you make resolving part of view, this is going to be enjoyable. So we take 54 newtons to the vertical, it will be 54 sine of 35 degrees. So that is going to be the component in the vertical, which I think is 54 sine 35, that is 30.97, which is approximately 31 newtons. To calculate the vertical component of the tension, so I will just call tension in the vertical is going to be, we have seen it is 54 sine of 35. Is it sine 35? Yes. 54 sine 35, which is equal to, which we have seen as 30.97, 30.97, which is approximately 31. It's approximately 30. Explain why the force on the sign at B does not have a moment. About point A. The force on the sign at B does not have a moment about point A because its line of action will actually be going through A. Because they said the force at B is only acting in the vertical. Since it is acting in the vertical, then its line of action passes through point A. That means the perpendicular distance is going to be 0. The perpendicular distance of the line of action of the force from B is 0 because the line of action goes through point A. So we can simply say the line of action of the force at B passes through point A. The line of action of the force at B passes through point A. The line of action of the force at B passes through point A. Or we can say the line of action of the force at B has zero perpendicular distance from point A, because moment is force times perpendicular distance. If perpendicular distance is 0, then the moment is 0. So the line of action of the force at B has 0 perpendicular distance. Zero perpendicular distance from point A. Therefore, it has no moment. By taking moments about point A, show that the weight W of the sign is 150. Let's go back to the diagram. We are taking moments about A, so the weight is vertically downwards. We can find its perpendicular distance here, which I think the perpendicular distance is 0.68 divided by 2, which is 0.34 meters. And the weight is causing a clockwise moment about point A. Then the 54 newtons is going to be causing an anti-clockwise moment about point A. But since I have the vertical component, I'll use the vertical component plus this perpendicular distance here, which is perpendicular distance of the line of action from point A, which is 0.68. So we have two forces which are causing moments. The perpendicular component, because the horizontal component will be acting towards point. It will be acting towards point B. So I will simply use the vertical component, which is having a perpendicular distance of 0.68. Alternatively, I could also have the horizontal component, which is also acting in this direction. Along the horizontal, there's that moment which is going to, the horizontal component is going to be 54 cos of 35. And this will be at a perpendicular distance, which is, this is the same as 0.68. So the vertical component, which is 54 sine 35, is causing a moment which is actually anti-clockwise. Then the horizontal component, because it will point to the left, it is also causing a moment which is actually anti-clockwise. Therefore, those two moments could be summed up, and we equate them to the moment due to the weight, which is actually clockwise. So we have that the weight, W, times its perpendicular distance, which is 0.34, that is clockwise, should be equal to the horizontal component of the weight of mean of 54, which is 54 cos 35, times its perpendicular distance, which is the same as 0.8 from point A, 0.68 from point A, plus the vertical component, which is 54 sine of 35, times its perpendicular distance from A, which is still in the horizontal, that is 0.68. Those will form the anticlockwise moments, and these will help us to find W for equilibrium. So we have said weight, which is W times the perpendicular distance, which was 0.34, should be equal to 54 cos of 35 degrees. That was the horizontal component. Multiply this by the perpendicular distance, which is 0.68, plus a 54 sine of 35, which was the vertical component, times the perpendicular distance, which is 0.68. So both the horizontal and vertical component were causing anticlockwise moments. That's why they are on the same side summed up. So we check our calculator. On the right hand side, we shall have 54 cos 35 times 0.68 plus, I'll open the brackets, 0.68 times 54 sine 35, which is 51.1. Then I'm going to divide both sides by 0.34, which is on the left hand side, to remain with the W. So I'm finding W as 150.4. So W is equal to 150.4, which is approximately 150 as required. 150 newtons as required. Calculate the total vertical force exerted by the wall on the sign at points A and B. The total vertical force. We have seen the weight downwards is 150. And we have also seen there's the force at B, they say the force at B only acts in the vertical. And we have only 31 newtons acting vertically upwards. We have the weight vertically downwards. So we can find out total force acting at A and B, which will be now the balance. The total force acting on A and B should be the balance from the difference between the weight downwards and the component of 54 newtons vertically upwards. So the total, and that force is going to be vertical for equilibrium. So total vertical force is going to be the weight downwards, which is 150, minus the component of 54 newtons upwards, which is 31. And that means the total vertical force is 120, and it is acting at A and B. Maybe it is vertically upwards to balance the weight downwards. The sign in B is held together by nuts and bolts. One of the nuts falls vertically from rest through a distance of 4.80 meters to the pavement below. The nut lands on the pavement with a speed of 9.2 meters per second. Determined for the nut falling from the sign to the pavement, the ratio change in gravitational potential energy over final kinetic energy. So first of all, we know that the change in potential energy is equal to mg times the change in the value of h. And we also know that kinetic energy is equal to a half mv squared. So we can find the ratio. We are going to divide mgh divide by a half mv squared. So this is going to be, m has cancelled, so we remain with 9.81 times h, which is 4.8, divided by a half, which is 0.5, times v, which is 9.2 squared. So we just substitute this in the calculator. 9.81 times 4.8 divided by 0.5 times 9.2 squared. So the ratio is 1.11, which we shall just quote as 1.1. think 4 marks is too much for that question. A sphere is a sphere in a liquid accelerates vertically downwards from rest. That means initial velocity is 0. For the viscous force acting on the moving sphere, state the direction. The sphere is accelerating vertically downwards. So let's assume this is a liquid and the sphere is here. If it is accelerating vertically downwards, it means the resultant force is downwards. So the weight is vertically downwards. We know that the upthrust is going to be upwards. It is always upwards. Because the motion is downwards, and viscous force is like friction, it opposes direct motion. So viscous drag is going to be upwards. So this is vertically upwards. Then the variation, if any, in the magnitude. Of course, the viscous drag increases with the speed. But remember, as the sphere moves downwards, the viscous drag is increasing, is in the opposite direction upwards. As the speed of the sphere increases downwards, it means the viscous drag will also increase in the opposite direction. It's like air resistance. Air resistance increases with the speed. So we can say that this one increases with velocity, or it will increase with the depth, because as depth increases, the speed is increasing, or it increases with the depth or with the time, because as time goes on, the sphere gains more speed. It means the speed is increasing. What is very important is the velocity, because the velocity is increasing as depth increases, or the velocity is increasing as time goes on. Okay, a man of weight 740 Newtons stands at a distance of 3.6 meters from end D of a horizontal uniform beam AD as shown here. So let's look at the diagram. The beam has a weight of 380 newtons, so this acts at the center, because weight of a uniform body acts at the center. So that distance is 9 divided by 2. That distance is going to be 4.5 meters. Even that distance from the other end is going to be 4.5 meters. The beam is supported by a vertical force Fb, and a vertical force Fc at pivot C. Pivot B is a distance of 2 meters from end M. Pivot C is a distance of 2 meters from end D. The beam is in equilibrium. This is very important. State the principle of moments. The principle of moment states that for a body in equilibrium, especially rotational equilibrium, for a body in rotational equilibrium, for a body in rotational equilibrium, the sum of clockwise moments, about a point equals to the sum of anticlockwise moments about the same point. This should have been, the moments could have been taken about the same point. The moments should have been taken, or must have been taken about the same point. By using moments about point C, calculate FB. So let's take moments about point C. So FC will have no moment because its line of action is through C. FB is going to be pulling the beam in that direction about point C, so that is causing clockwise moment. The weight is going to be pulling the beam in this direction about point C, so that is anti-clockwise. 750 is also pulling the beam in that direction about C, so that is also anti-clockwise. So for equilibrium, the sum of these moments should be equal. So we have for clockwise moments, we shall have FB times its perpendicular distance, which is 9 meters minus the 2 on this end, again minus the 2 on the other end. So that's that is going to be FB times 5.0. That is clockwise. For anti-clockwise, we have 750 times its perpendicular. This was clockwise, so we have 750 times its perpendicular distance, which is 3.6 minus 2. We want the distance always to the pivot, to point C. That is 3 minus 2. And we also have 380 newtons. That one acts at the midpoint. Its perpendicular distance is going to be 4.5. The distance from the center to the other end is 4.5 minus the distance from C to D, which is 2.0. So this one is 3.6 minus 2, that is 1.6. And then 4.5 minus 2, that is 2.5. So these are the moments that we are going to sum up to as the anti-clockwise moments. So let's answer the question. So we have seen that FB times its perpendicular distance, which is 5.0, is going to be equal to 750 times its perpendicular distance, which we have seen as 1.6, plus 380 times its perpendicular distance, which we have seen as 2.5. And when we check this in the calculator, 750 times 1.6, that's what we get, plus 380 times 2.5, we get that, divide by 5. That is 430. So FB is exactly 430 without even rounding off. The man walks towards end D. The beam is about to tip when FB becomes 0. The beam is about to tip when FB becomes 0. It's about to tip when FB becomes 0. Note that the man is moving towards end D. The man is moving towards end D, and the beam is about to tip when FB becomes 0. Okay? Determine the minimum distance x from end D that the man can stand without tipping the beam. So just repeat the moment, but this time the man is moving towards end D and we want FB to become 0. So let's say the man has moved is a distance, let's say, because the man is moving towards end D, let's say the man has reached here, where this is at a distance of x. So the man is here. The man is here, where he has moved the distance x is at from points. That means the distance because we want to find the distance from end D, let's change the position of x. Let's put x at the other end. Because when I put it here, I may not use it for in calculations. What has happened? Because we want the minimum distance from end D, let's call this x, the distance x. So that means the man is now standing a distance which is 2 minus x from C. Remember the moment, remember this one is becoming 0. We want the minimum distance when this becomes 0 but the beam does not tip. because as the man moves towards end D, the distance, the force FB is decreasing. So we are again taking moments about C. By taking moments about C, taking moments about C. So since the man has now crossed the pivot, C is on the other side, so his 750 is now here. So 750 is now there. It is causing an anti-clockwise a clockwise moment. So this side, now the weight, this one is no longer there. We only have 8 newtons. Remember, this one is becoming 0. So 750 is now on the right hand side of position C, and is causing a clockwise moment. So 380 newtons is the only one causing an anti-clockwise moment. 380 newtons, its perpendicular distance will remain 4.5 minus 2, which is 2.5. But 750, its perpendicular distance will now be 2 minus x. So by taking moments about C, we shall have that clockwise moment, that is 750 times its perpendicular distance 2 minus x, is going to be equal to anti-clockwise moments, which is 380 times perpendicular distance, which is 2.5. So we now have that 380 times 2.5 divided by 750. So that's what we have. So we have that 2 minus x equals to 19 over 15. So I want x. So x is going to be 2 minus 19 over 15. So I'll say 2 minus the answer, which is 11 over 15, that is 0.73. So this is 0.73. 0.73. So that is giving us 0.73. By the alternative, we would take moments about D. We would take moments about D. We would take moments about D. In that case, FC will have a moment which is clockwise. Then the man will have a moment which is anti-clockwise about D. And then 380 newtons will have a moment about D which is anti-clockwise. So in that case, we shall say for the man, it is anti-clockwise now about D. So moments about D. Let me try to take moments about D. I've put a lot of things in this diagram just for understanding. Moments about D. The man, if I take moments about D, let me erase something here. If I take moments about D now, it means the man's moment about D is going to be in that direction, which is anti-clockwise. So that will be 750 times the perpendicular distance from D, which will be x. Then the weight of 380 newtons is still anti-clockwise, plus. So this will be 380. This time the perpendicular distance from D is 4.5 because it was at the midpoint. That is also anti-clockwise. Then force at C will be clockwise. Which force is the force at C is clockwise? Which force is going to, since we have FB, then the force at C is going to be 380 newtons plus 750. Let's check that. 380 plus 750. That is 1070. Because FB is becoming 0, the force at C is going to be the sum of the forces downwards. So the force at C is the sum of the forces downwards. So the force at C is actually causing a moment which is in that direction, clockwise about point D. So this will be equal to F at C, which is equal to 380 plus 750. We sum up the forces, and the perpendicular distance is 2 from point D. So we can now check. We can now check this on our calculator. So we have 350, which is, we have got the answer as that. Then times 2. Then we shall subtract 380 times 4.5. I'm collecting like terms. Then we shall divide by 750 and we get 0.73. So it means x is 0.73 in meters. Determine the SI base units of moment. We have seen more SI base units in a unit called physical quantities. So moment, we know that moment is a product of force and perpendicular distance. So moment force is going to be kilogram meters per second squared, then times perpendicular distance, which is in meters. So you notice that this simplifies to kilogram meters squared per second squared. So that is kilogram meters squared per second squared. A uniform square sheet of card ABCD is freely pivoted by a pin at point P. The card is held in a vertical plane by an external force in the position shown in the figure. Okay, so the card is pivoted at point P here. That's where the pin is, at point P. The card has a weight 0.515, which may be considered to act as the center of gravity. Each side of the card has a length of 17 centimeters. Point P lies on the horizontal line AC and 4 centimeters from corner A. Line BD is vertical. Line BD is vertical. The card is released by removing the external force. The card then swings in a vertical plane until it comes to rest. Okay. Capture the magnitude of the resultant moment about point P acting on the card immediately after release. So we want, this is the pivot. Of course, the weight has a perpendicular distance from the pivot. So the weight is going to cause a clockwise moment about point P. So we just need to find that distance. If this is 17, AB is 17, and the card is square, so we just look for the diagonal. We just look for the diagonal. Let's find this distance. This is also 17. Okay, so let me find this distance here, the whole distance AG. So distance AG, if I use the angle 45 degrees, AG is in the adjacent, AB is hypotenuse. So I'll say adjacent hypotenuse, that is cos. Cos of 45 is equal to AG divided by 17. So it means distance AG is equal to 17 cos of 45. That means the distance P to G is going to be 17 cos 45 minus 4 centimeters, because I want the perpendicular distance of the weight from point P. So the distance of the center of gravity from P is equal to the distance which I've called G to P, which we have seen is 17 cos 45 degrees minus 4.0. That is the distance. So we want now the moment. The moment is equal to the force times the perpendicular distance, and the force is 0.15, which is the weight, times the perpendicular distance, which is 17 cos 45, then minus 4. So let's check this. I'll start with the distance, which is 17 cos 45 minus 4. Then I multiply this by 0.15, which is equal to that 1.2 times, oh, by the way, this was in centimeters. So I will say this is times 10 power negative 2 because it was in centimeters. So let me say 117 cos 45 is that one minus 4, it is that one. That is the distance. The answer times 1 exponent negative 2, then times 0.15. So that is 0.012 or 1.2 times 10 power negative 2. 0.012 or 1.2 times 10 power negative 2 Newton meters. Explain why, when the card has come to rest, its center of gravity is vertically below point P. Because when the card comes to rest, its line of action will actually be through P. The line of action of the weight will be acting through P. So it means the weight does not have a moment about P anymore. Or you can talk about the distance. When the card comes to rest, the distance between the line of action of the weight and the pivot will become 0. So it means the weight will have no moment anymore. So we are saying, they said, explain why, when the card has come to rest, its center of gravity is vertically below point P. So we simply say the distance between the line of action of the weight and the pivot, which is P, is going to be 0. Is 0, so the weight has no moment. The weight will not have a moment when the card comes to rest because the distance of its line of action from point P will now be 0. Or you can think about the line of action being through the line of action of the weight being just through point P. The line of action of the weight, the line of action of the weight acts through the pivot. So it means the weight does not have a moment about P. Its center of gravity is going to be below point P because when it comes to rest, the line of action of the weight will be acting through the pivot, so the weight does not have a moment about P. A floating cylinder is attached by a cable to the bottom of a river as shown in the figure here. The sphere is in equilibrium. This is very important. The sphere is in equilibrium with the cable at an angle of 75 degrees to the horizontal. Assume that the force on the sphere due to the water flow is in a horizontal direction. The radius of the sphere, so the force due to the water flow is in a horizontal direction. The radius of the sphere is 23 centimeters. The sphere is solid and is made from a material of density 82 kilograms per meter cubed. Show that the weight of the sphere is 41 newtons. So to find the weight is going to be mg. the weight is going to be m times g. We need the mass. And the mass is going to be density times volume. So this will be density times volume, then times g. That is going to be the weight. But of course, we know the volume. Since it is a sphere, volume is 4 over 3 pi r cubed. So this is going to be density times the volume, which is 4 over 3 pi r cubed, then times, that is the volume, then times g. So we can now substitute to find the weight. So the weight is going to be equal to density. Density is 82. Then let me first add there g, which is 9.81. Then times 4 over 3 pi. The radius is 23 centimeters, so I'll set 23 times 10 power negative 2, and this is going to be raised to power 3. So we have 82 times 9.81 times 4 pi. Divide by maybe 3, then times, open brackets, 23 exponent negative 2, and this is raised to power 3. So that is giving us 40.997. So this is 40.997, which is approximately 41 in newtons. The tension in the cable is 290 newtons. Determine the upthrust acting on the sphere. Determine the upthrust acting on the sphere. The tension in the cable is 290 newtons. Determine the upthrust acting on the sphere. So if the tension is 290 newtons, the upthrust acts in the vertical direction. So the tension in the sphere, of course, because the water is that side, the tension is going to be downwards. Tension is going to be downwards, and this is 290. Tension is 290. So we are going to resolve this in the vertical plane because upthrust acts in the vertical plane. We have to resolve T in the vertical using 75. T in the vertical will be T sine 75 degrees. But remember, the weight is also acting downwards, which is 41, and it is in equilibrium. So it means the upthrust plus the weight, the upthrust downwards plus the component of the tension downwards should be equal to, the upthrust upwards should be equal to the component of the tension downwards plus the weight. So the weight downwards plus the vertical component of the tension should be equal to the upthrust. So we need the vertical component of the force in the force in the vertical. So the tension is acting at an angle of 75 degrees, so its component is going to be 290 sine 75 in the vertical. When we add it to the weight, then we get the upthrust. Note that the tension is downwards because the direction of the water is actually pulling away the solid sphere. So the tension is downwards. And the weight of the sphere is also vertically downwards. So the sum of the two forces vertically downwards should be equal to the force upwards, which is the upthrust. So we shall simply say upthrust is equal to the component of the tension in the vertical, which is 290 sine of 75 plus the weight, which is 41. So this is going to be 290 sine 75 plus 41, which is 321. So that is 321, which is approximately 320. So what is the origin of the upthrust? If we have an object submerged in a liquid, there is a pressure due to the liquid at the bottom and there is a pressure due to the liquid at the top. The difference in the pressure due to the liquid at the bottom and the pressure due to the liquid at the top is actually the origin of the upthrust, because that difference in the pressure multiplied by the cross-sectional area will actually be the upthrust according to Archimedes' principle. So the pressure on the lower surface pressure on the lower surface of the sphere is greater than the pressure on the upper surface. So we know that the pressure at the bottom, where H2 is greater than H1, the pressure at the bottom is going to be H2 density times G. H2 is greater than H1. So it means the pressure at the bottom is greater than the pressure at the top, and that difference in the pressure is responsible for the upward force acting on the sphere. We know that pressure increases with depth in a liquid or in a fluid. Define the torque of a couple. Torque can be used in the place of moment. In other words, we are defining moment of a couple. Remember, a couple, these are two forces. These are two forces acting in opposite directions whose line of action can never meet. So, a couple, the torque of a couple or the moment of a couple is going to be the product of the magnitude of one of the forces product of the magnitude of one of the forces of one force and the perpendicular distance between the two forces. Perpendicular distance between the two forces. So a couple constitutes two forces. There are two parallel forces acting in opposite directions whose the lines of action of these two forces can never meet. Those constitute what we call a couple. So the product of one of the forces and the perpendicular distance between the two forces is what we call the moment of a couple or the torque of a couple. A torque, a torque wrench is a type of spanner for tightening a nut and bolt to a particular torque, as illustrated here. The wrench is put on the nut and a force is applied to the handle. A scale indicates the torque applied. The wheel nuts on a particular car must be tightened to a torque of 130 Newton meters. This is achieved by applying a force F to the wrench at a distance of 45 centimeters from its center of rotation, C. This force F may be applied at any angle theta to the axis of the handle as shown in the figure. For the minimum value of F to achieve this torque, state the magnitude of the angle theta that should be used. If we want to apply a small value of F, then this force must be acting vertically downwards onto this handle. So F must be acting vertically downwards onto this handle instead of acting at that angle. That means to apply a minimum value of F, then the magnitude of the angle theta that should be used is going to be 90 degrees. 90 degrees. Then calculate the magnitude of F. Calculate the magnitude of F. Remember to tighten. The car must be tightened to a torque of 130 Newton meters. So this force here, when it is acting vertical, the perpendicular distance is 45 centimeters. Therefore, the force times the perpendicular distance should give us the minimum, the torque, which is 130 newtons to tighten the nut. So we can simply say F times its perpendicular distance, which is 45 divided by 100 to change it into meters, should give us a torque of 130 for the nut to be tightened. So that means 130 times 100 divided by 45. I just divided by 45 by 100 to change it from centimeters to meters. So F is equal to 88.8 recurring, which is approximately 290 newtons. State the two conditions that must be satisfied for a body to be in equilibrium. Number one, there should be no resultant force. No resultant force on a body in any direction. There should be no resultant force on a body in any particular direction, and also there should be no resultant moment or torque. There should be no resultant moment or torque. There should be no resultant moment or torque for this body to be in equilibrium. Three coplanar forces act on a body that is in equilibrium. Describe how to draw the vector triangle to represent these forces. We made a diagram. So how do we draw a vector triangle to represent the three forces? Coplanar means they are in the same plane. Remember, forces are going to be represented by lines with arrowheads to show the direction. And the length of the lines represents the magnitude, and the direction of the arrows represents the direction of the force. Remember, the vectors are joined head to tail. So each force can be represented by a side of a triangle. Each force can be represented by the side of a triangle. By an arrow, in magnitude and direction. The side of the triangle will show the magnitude, and the arrow will show the direction. Magnitude and direction. Remember, the arrows are joined head to tail. The arrows are joined head to tail. So what I'm saying is I'll draw a demonstration here. This could be one of the vectors, and this could be another one, and this could be another one. So the sides, the vectors, the forces are represented by the sides of the triangle, and because it is in equilibrium, the arrows are going to be in that pattern so that they form a closed loop in that pattern. The vectors are joined head to tail. So I could just draw the diagram without writing anything because the diagram tells everything. The triangle is closed, the arrows are joined head to tail, so those are forming, those forces are actually in equilibrium. State how the triangle confirms that the forces are in equilibrium if the triangle is closed. If the triangle is closed, like the one which we have drawn, if the triangle is closed, then the forces are in equilibrium. So imagine if you are drawing three vectors to scale and they form a closed triangle after joining them head to tail. Then it means they are acting on a body that is in equilibrium. A weight 7.0 newtons hangs vertically by two strings A, B, and AC as shown in the figure. For the weight to be in equilibrium, the tension in AB is T1 and in string SC is T2. On the figure, draw a vector triangle to determine magnitudes T1 and T2. So we can draw a vector triangle. We can draw a vector triangle on this figure. So we fix one vector. We can fix T1 and transfer T2. So I'll prolong this line vertically upwards, and I'll just use a protractor, a set square and a protractor, and I slide it upwards from T1. From T2, I slide it to T1. In other words, I've transferred T2 onto T1. So this is going to be T2 without changing the direction. They are parallel. So the vector triangle we are looking for is going to be this one. Or you could transfer T1 to the other end of C. So this is the vector triangle. And we can find these angles. This is 50 degrees. We can find this. Of course, if this is 50, this is going to be 95 degrees. So this is the weight downwards, which is actually 7 newtons. So I think we are going to use this vector triangle to find the magnitude of T1 and T2. You can use calculations. Some people would prefer to use sine rule, cosine rule, and so on and so forth. But we can draw this to scale. If you want to use sine rule, some people would say T1 over 50 should be equal to T2 over 35. Sine 50 sine 35 should be equal to 7.0 over sine 95. But I don't want to use that. I want to use, let's just check one using the sine rule and we see what happens. So it means T1 is going to be 7 over sine 95 times sine 50. 7 divided by sine 95 times sine 50, which is 5 point, T1 is 5.4. So T1 is 5.4. You can check also T2. T2 will be 7.0 over sine 95 times sine 50. 7.0 divided by sine 95 times sine 35, which is 4.0, which is true. Those answers are true. But since they want us to use the triangle, you could use the sine rule, no problem, which gives you T1 as 7.0 over sine 95 times sine 50, and T2, which will be 7.0 over sine 95 times sine of 35. But we want to draw this to scale. I want us to draw this to scale. So let's see how to draw this to scale. I am not sure if the angles are on scale. Using my protractor, let me verify the angles if they are to scale. If they are not to scale, I'm going to draw a different diagram. Surprisingly, the angles are to scale. So I've seen 35 is to scale. Let me check 50. 50 is also to scale. So we are going to just use the diagram as it is. So let's use the diagram as it is to draw this to scale. So I have drawn a vertical line. On this vertical line, I will choose 1 centimeter to represent 1 Newton. 1 centimeter is going to represent 1 Newton. That means on the vertical, I'm going to measure 7.0 Newtons. So on the vertical from A to the top, I'm measuring 7.0 Newtons. Using my ruler from A upwards, I'm measuring off 7.0 Newtons, which is around here. So that is 7.0 Newtons. And at this point here, where 7.0 Newtons, I'm going to measure off the angle which T2 makes with that 7.0 Newtons with the vertical. And this angle is 50. So I'll put a protractor here and measure off 50 degrees from the vertical. Locate where T2 will be. Remember, this is T2. I want to transfer it now here. So I'll put a protractor where 7.0 stops. So I've found 50 degrees and I'll put the protractor. I'm trying to look for instruments that can be used on the laptop, such as the ruler and the protractor, but I've not yet managed to download any. Let me draw a better line. So this angle is 50 degrees. It is the same as the one at the bottom here. So this is going to be T2 without even changing direction. That will be T2. So it means T1 stops here. So the triangle we are looking for starts from A to this point here up to that point there. So I can even rub off the remaining part, but it is not necessary. So what is T1? To measure off T1, I know the scale 1 centimeter represents 1 Newton according to what I've used. So I'll just measure the length of T1 as part of that triangle, where T1 stops as part of that triangle. So from A to that point where T1 stops, and it is exactly 5.4. So that is 5.4 centimeters, which is 5.4 Newtons. Then I also measure the line where I have put T2. I measure the line, find T2. So T2 is going to be equal to, I'm measuring that line, and it's surprising, it is exactly 4. So this is 4.0 Newtons. 1 centimeter was representing 1 Newton. So when I draw the triangle to scale, it is giving me 4.0 centimeters for T2, which is 4.0 Newtons. 5.4 centimeters for T1, which is 5.04 Newtons. So from the scale, so by scale, where 1 centimeter represents 1 Newton, I'm getting T1 as 5.4 and T2 as 4.0. In the book, you may not exactly get the same answer, but there's an allowance. The answers will still be around 5.4 and 4.0. Okay, so the examiner will want to see your scale. The examiner will want to see the scale before he checks the answers. Okay, since they wanted us to use the triangle, I think that is all. You could also find one value of t using the sine rule and then use the cosine rule to find the other value. Or, since you know this angle as 95 degrees, you know that angle as 95 degrees, and you know this side as 7.0 centimeters, you could come up with equations, but that would be a long process. Okay. By reference to figure 2.1 suggests why the weight could not be supported with the strings AB and SC both horizontal. Suppose these strings were in the horizontal. It means the vertical force downwards of 7 newtons will have nothing to support it in the vertical. Therefore, the beam cannot be in equilibrium. So it means forces in the strings would be horizontal. Forces in strings would be horizontal, so no vertical force, no vertical force. There will be no vertical force to support the weight. If the forces in the strings were horizontal, they would have no vertical components. So there would be no vertical force to support the weight. Therefore, equilibrium could not be achieved in that case. Explain what is meant by center of gravity. So we are now used to this. This is a point where all the weight of an object may be considered to act. That is center of gravity. Point where all the weight of an object may be considered to act. Then moment of a force, that is force times perpendicular distance of the line of action of the force from the pivot. So this is force times perpendicular distance this is C, perpendicular distance of the line of action of the force to the pivot or from the pivot of the force to the pivot. Force times perpendicular distance of line of action of force to the pivot, that is moment of the force. The student is being weighed. The student of weight W stands 0.3 meters from end A of a uniform plank AB as shown there. The plank has weight 8 newtons, length 2 meters. That means the distance of the plank from the center of where its weight is 1 meter. You must be noting that. The pivot P supports the plank and is 0.5 meters from end A. So we can see the pivot here at point P. A weight 70 newtons is moved to balance the weight of the student. The plank is in equilibrium when the weight is 0.2 meters from end B. State the two conditions necessary for the plank to be in equilibrium. We have already mentioned the two conditions. There should be no net resultant force is 0 or no resultant force. Net resultant force is 0. The net or resultant moment is 0. Resultant moment is 0 or resultant torque is 0. What does that mean? The sum of clockwise moments should be equal to the sum of anticlockwise moments about the same point. Determine the weight W of the student. Determine the weight W of the student. So let's determine the weight of the student. So we can take moments about maybe about P. We can take moments about P. So the student, if P is the fixed point, the student is causing anticlockwise moment about P. 80 newtons will cause clockwise, 70 newtons will cause clockwise. So I'll take moments about P. So taking moments about P. The weight of the student is W times the perpendicular distance from P. Perpendicular distance is going to be this one, which is 0.5 minus 0.3, that is 0.2. So that is times 0.2. It is the only one causing anticlockwise moments. Then 80 newtons is causing clockwise moments. Its perpendicular distance is this one here. Remember, the 80 newtons was at the center of the beam. So 1 meter minus 0.3 is going to be the distance of 80 newtons from, no, 1 meter minus 0.5 is going to be the perpendicular distance of the weight from point P. 1 meter minus 0.5 is 0.5. So that would be 80 times the perpendicular distance, which is 0.5, plus 70, the weight of 70 newtons. Its perpendicular distance will be this distance here, which is going to be, that distance can be 2 meters minus 0.5 minus 0.2 the other side. It is 2 meters minus 0.5 on the left hand side minus 0.2 on the other end of B, So this gives you 2 minus 0.7, which is 1.3. So this is plus 70. Its perpendicular distance is 1.3. So this is going to be, I think this is 40 plus 70 times 1.3. I think that is 90 something, 91. So 0.2 W is equal to that. So we now add and divide. So 91 plus 40 divided by 0.2, that is 655. So W is 655 newtons. If only the 70 Newton weight is moved, there is a maximum weight of the student that can be determined using the arrangement shown. State and explain one change that can be made to increase this maximum weight. If we only move this 70 Newton weight, there is a maximum weight that can be determined by this arrangement. So we want to determine, state and explain one change that can be made to increase the maximum weight which can be determined. It means that if we move 70 newtons towards B, it comes to the end. And that means there's a maximum weight it can determine for the student. So if we want to increase the maximum weight, then it means we must move the student further towards end A, so that we increase the anticlockwise moment. Or we can move the pivot closer towards 70 newtons so that we still increase the anticlockwise moment. Moving the pivot to the left is going to give a greater clockwise moment. So when we move the pivot towards the left, we have a greater clockwise moment. It means we can still support more weight on the left hand side. We can move the student towards the pivot to reduce the anticlockwise moment, so that it means 70 newtons can now measure a greater weight. So we are saying, number one, we can move W to the right, which gives a smaller anticlockwise moment. Move W to the right or towards the pivot. Move W to the right, which gives a smaller anticlockwise moment. When you move W to the right, it will give a smaller anticlockwise moment, allowing for more weight to be added. So it means the maximum weight can be increased. Alternatively, we can move the pivot to the left. Moving the pivot, that is point P, moving the pivot to the left gives a greater clockwise moment. Moving the pivot to the left, it is going to make the moment on the right hand side to be greater because of the distance being greater. Moving the pivot to the left gives a greater clockwise moment. Gives a greater clockwise moment. That means it is a smaller anti-clockwise moment. Okay, so that means the maximum weight can be greater if we move the pivot to the left. A climber is supported by a rope on a vertical wall as shown in the figure. The weight W of the climber is 250 newtons, so W is 250 newtons. 520 newtons. The rope of negligible weight is attached to the climber and to a fixed point P, where it makes an angle of 18 degrees to the vertical. The reaction force R acts at right angles to the wall. The climber is in equilibrium. The climber is in equilibrium. That means the resultant force is zero, resultant moment is zero. State the conditions necessary for the climber to be in equilibrium. Number one, resultant force 0. Resultant force equals to 0. We have also seen the resultant moment should be 0. The resultant force should be 0, resultant moment or resultant torque should be 0. Then complete the figure by drawing a labeled vector triangle to represent the forces acting on the climber. So the weight has been given vertically downwards, and then of course we join vectors head to tail. So the horizontal, the normal reaction, the normal reaction from the wall will be R is there, and then the tension will be there, which is T. Alternatively, we can have the weight vertical downwards and the normal reaction, which I'll put this one on top, which is because we join head to tail, and then we shall join the tension will be here in that direction without changing its direction. So this will be tension, that will be R, this is W. Tension R, that is W. So we have two options. We have two options. So I will take the obvious option. I will draw R at the bottom. Because the angle is very small, I can't draw R when it is very long. So this will be the tension. This is going to be R. That is going to be our diagram because they said it is a labeled vector triangle, so you have to put the R and T labeled. Resolve forces or use your vector triangle to calculate the tension T in the rope. So if you choose to resolve forces, then it will be very easy. If you choose to use the triangle, it is also fine because the weight has been given as 550. The weight has been given as 550, so you could have drawn the triangle to scale if you want. This is 520. You could draw the triangle to scale, maybe 1 centimeter to represent maybe let's say 100 newtons. so that 550 is 550 will be 5.2 centimeters. But I'll resolve because resolving is very easy. So let us resolve. Resolving T, if I draw a vertical line here, you notice that this angle is also going to be 18. So when I resolve T in the vertical, it points upwards, and you see that it will be T cos 18 in the vertical. When I resolve T in the horizontal using the angle 18, it will now be T sine. This will point to this side, and that will be T sine 18. So for equilibrium, T sine 18 should be equal to R, and T cos 18 should be equal to W. So I will simply say, resolving, we have T cos 18 is equal to W, and T sine 18 is equal to R. So starting with the T cos 18 equals to W, remember W is 520. So it means, let me first ignore the second part because it is not necessary here. So it means T is going to be 520 divided by cos of 18. So that is 546.76 or 547. 547 newtons. Then for the normal reaction, we have seen that when we resolve T in the horizontal, it will be T sine 18 is equal to R. We have already got T. So R is going to be 547 sine of 18. So answer times sine of 18, which is 169. The climber moves up the wall and the angle the rope makes with the vertical increases. Explain why the magnitude of the tension in the rope increases. So we have seen that T is equal to, when we resolve the vertically upwards, we saw that T cos theta is equal to the weight, which means T is equal to the weight over cos of theta. They have told us the angle increases. If the angle increases, if theta becomes larger, I think cos theta becomes smaller. That means the tension decreases. The tension becomes smaller because, or by the tension becomes bigger because cos theta becomes smaller. When we divide with a smaller quantity, the value of T is going to be larger. So the question is asking us to explain why the magnitude of the tension in the rope increases. So we have that tension is equal to weight divided by cos of theta. So as the climber moves up, theta becomes larger. So theta becomes larger. Theta becomes larger. So cos theta becomes smaller. So cos theta is smaller. You can check that with the calculator. As theta becomes larger, cos theta becomes smaller. So cos theta becomes smaller. Hence T is larger. Remember, cos theta is larger when theta is 0 because cos of 0 is 1. So T becomes larger because cos theta becomes smaller as theta itself becomes larger. That's why the tension is increasing. Two tugs pull a tanker at a constant velocity in the direction xy as represented by the figure. We can look at the figure. So tugger 1 pulls the tanker with a force T1 at that angle, tug to XY, tugger 2 pulls the tanker with a force T2 at that angle. The resultant force R due to the two tugs is 25 times 10 power 3 newtons in the direction XY. By reference to the forces acting on the tanker, explain how the tanker may be described as being in equilibrium. It is moving at a constant velocity, so it means the sum of the forces T1 and T2 it must be equal and opposite in direction. Actually, maybe there is going to be friction here because we don't see any other force that will balance T1 and T2 in the horizontal. So we can say since it's moving, it moves at a constant velocity. Since it moves at constant velocity, the sum of T1 and T2 is equal and in opposite direction to the frictional force. So the sum of the two forces, T1 and T2, should therefore be equal to the frictional force, but in opposite directions if the tanker is in equilibrium. Complete the figure to draw a vector triangle for the forces R, T1, and T2. So the resultant is here. So we have to fix one of these forces, either T1 or T2. We have to fix either one of these forces, T1 or T2. If I fix T2, it means if I fix T2, it means I will bring T1 so that it is parallel to its initial position. So that will be T1. And I may draw this to scale. I'll draw this to scale. So since they have already given us a horizontal line, we can say 1 centimeter, because the next part may be wanting us to find the resultant. So using a scale, we can say 1 centimeter represents, let me see, 25,000 divided by 500, or 25,000 divided by 5,000, that is 5. Okay, I want it to be at least 10 centimeters. So I'll say 25,000 divided by 2,500. That is 10. So I'll say 1 centimeter is representing 2,500 newtons. That means 25,000 is going to be 10 centimeters. So I'm going to measure 10 centimeters on this line. So 10 centimeters on this line, or I make it even longer to 10 centimeters, but it's already longer. So I will say this is the starting point. From there, I will measure 10 centimeters, and 10 centimeters stops here. So I'm going to put the I'll put the diagram on top. I'll put the diagram on top rather than the bottom. So I'll put the protractor here and measure off 25 degrees to find T1. I mean T2. Okay, T1. So from the horizontal line, I'm measuring 25 degrees, and 25 degrees is somewhere there. So using my ruler, I'll draw a line which makes 25 degrees with the horizontal. That is the line. So this angle is 25. degrees, and I know that T1 is somewhere on this line. So T2 makes an angle. Let's see which angle does T2 make with the horizontal. If this is the horizontal, that is the horizontal line, T2 is making an angle with the horizontal, which is still 15 degrees. Because this angle here is the same as that one. So I'm going to measure 15 degrees from the horizontal where the 10 centimeters stop on the horizontal line. So here I'll put a protractor and measure 15 from the left. So I'm measuring off 15 from the left, and 15 is somewhere here. 15 is somewhere here. So I'll do a line for 15 degrees, making 15 degrees with the horizontal, and that is the line. So it means now T2, without reversing its direction, T2 is going to be here. So the triangle stops there. They are meeting at that point here. So if I want to measure T1 in the next part of the question, I can measure the distance from this point to this point for T1. So T1 is going to be equal to, I'll multiply that by the scale. So let me measure the length only for the triangle. So that is 4.3. So T1 is 4.3 centimeters, then times the scale, which is 2,500. So that is 4.3 times 2,500. That is 10,750. 10,750 newtons. Then I can also find T2. T2 is going to be equal to the length. I measure the length for T2 from here up to this point. So that is 6.4. So T2 is 6.4 in centimeters times the length. Times the scale, which is 250. 2,500. 6.4 times 2,500. That is 16,000 newtons. So that was using a scale diagram. Because I know the next part of the question wants T1 and T2, you can just get from the scale diagram. In other words, I took advantage of this part where they told us to draw a vector triangle, and I drew a vector triangle to scale. However, in the space provided here, I'm simply going to resolve. So we have, this is XY. We have T1 here, which is at an angle of 25 degrees. We have T2 here, which is at an angle of 15 degrees. 15 degrees. That is T2. The resultant here is 25. This is 25 times 10 power 3. So it means when I resolve T in the horizontal, T1 in the horizontal will be T1 cos 25 plus T2 in the horizontal will be T2 cos 15. The resultant of these ones in the horizontal is actually 25. So this is 25 times 10 power 3. That is in the horizontal. If I resolve them vertically, T1 in the vertical to be T1 sine 25, and this will be acting upwards. T1 vertically will be upwards, that is T1 sine 25. T2 vertically to be downwards, that will be T2 sine 15, and this should be equal. So this is going to be T2 sine of 15. So I'm going to solve these two equations. So I will say that T1 is equal to T2 sine 15 divided by sine 25. And I will substitute for T2. I will substitute for T1 into this equation here. So I'll say T2 sine of 15 over sine of 25 times cos of 25 plus T2 cos of 15 should be equal to 25 times 10 power 3. I've just replaced T1 here with the expression for T1 that I've made the subject there. So the common factor is T2. I'll just say T2 equals to, I combine all these and I divide 25 by the resultant. So in brackets, I have sine of 15, that is sine of 15 times cos of 25 divided by sine of 25 plus cos of 15. That is what I have. On the left hand side, that's what I have. If I combine these sines and cos, then I have 25,000 divided by the answer. That is T2 is 16436. 16436.9, or approximately 16,400 newtons. And from the scale diagram, T2 was 16,000. So we are approximately there. Then T1, we substitute T2 into T1. T1 will be equal to that answer times sine of 15 divided by sine of 25. And we have 10,066. In our answer, we got 10,750. So here it is 10,066. So this is approximately 10,000 newtons. So those are the values of T1 from resolving. Okay, next, show that the pressure P due to a liquid of density rho is proportional to depth h below the surface of the liquid. So we know that pressure is the force acting normally per unit area, so immediately we can write the formula: pressure is force over area. What will be the force? Our force is going to be equal to the weight. In this case, our force will be the weight, which weight is equal to mass times g. And the mass is density times volume, and yet the volume is equal to cross-sectional area times the height h. So it means now we are going to substitute backwards. So the force is equal to the weight, which is density, times the volume, which is cross-sectional area, times h, then times g. So that is our force. So it means the pressure is going to be force over area, which force is density times area times h times g, divided by the cross-sectional area A. And we see that area cancels, so the pressure is equal to density times h times g as required. So the pressure is due to the liquid of density rho is proportional to the depth h below the surface. The pressure of the air at the top of the mountain is less than that at the foot of the mountain. Explain why the difference in air pressure is not proportional to the difference in height as suggested by the relationship in B. So we have seen that pressure is equal to H density times G. They are saying explain why the difference in air pressure is not proportional to the difference in height as suggested by the relation. Of course, the problem comes with the density. The density of the air also changes with the height. And if the density is not constant, it means the pressure is not going to be just proportional to H. So pressure is equal to H rho G, and density changes. The density of air changes with the height. The density of air changes with the height, and since density is not constant, since density is not constant, pressure cannot be proportional to the difference in height. Pressure cannot be proportional to the difference in height. Although G may be constant, but the density of air changes with height. And since the density changes with height, in fact, the density decreases. It may be assumed to decrease linearly, but may not be decreasing linearly. So since the density is not constant, the pressure cannot be proportional to the difference in height. Distinguish between mass and weight. We know that mass is a property of the body resisting changes in motion, or mass is a quantity of matter in a body. Mass is a measure of inertia to changes in motion. That is mass. So mass is a property of the body resisting changes in motion. That is mass. Mass is the quantity of matter in a body. Quantity of matter in a body. That is mass. Or you can say mass is a measure of inertia. Measure of inertia to changes in motion. That is mass. Then weight, of course, weight is the force due to gravity. This one is the force on a body due to gravity. The force on a body due to gravity, that is the weight. It is the force due to the gravitational field. The force on a mass due to the gravitational field. That is weight. The pull of gravity on an object, that is what we call the weight. Okay, an object O of mass 4.9 kilograms is suspended by a rope A that is fixed at point P. The object is pulled to one side and held in equilibrium by a second rope B as shown here. So you can see the diagram. On the figure 2.1, draw arrows to represent the directions of all the forces acting on object O. Rope A is at an angle theta to the horizontal and rope B is a horizontal. The tension in rope A. So because the object is here and has a weight vertically downwards, I'll call this the weight, which is W. Of course, there will be tension in that rope. I'll call that one tension in B. There will be tension in this rope away, which is going to be tension in A. So on the figure, draw arrows to represent the directions of all the forces acting on the object. So we have one for weight vertically downwards. Tension in B is in that direction. Tension in A is going to be in that direction. Then calculate the angle theta. There is equilibrium here, so this is very important. It's held in equilibrium. The mass is 4.9 kilograms and is held in equilibrium. So it means we can use simple relations. We can use simple resolving to find the angle theta. So first of all, they have given us the weight, the mass. So weight is m times g. So I'm going to resolve, since the tension in one of these is given, tension in A is 69, so I'm going to resolve vertically upwards. So let me put here vertical line. When I resolve tension in A, this is, remember, 69. So this will be 69. Using the angle theta, this will be 69 sine theta. For equilibrium, 69 sine theta upwards will be equal to the weight. So 69 sine theta should be equal to the weight, which is m times g. So 69 sine theta is equal to the weight. The mass was 4.9 times g, which is 9.81. So I'm just pressing my calculator. 4.9 times 9.81 divided by 69. Then I get the sine inverse. Sine inverse of the answer, or the arcsine of the answer, which is 44.1. So theta is 44.1. Then the tension, so it means I'm going to resolve in the horizontal. The tension T. T is the tension in B, so I called it TB. Let me reverse it to be T, just T. So I have to resolve 69 into the horizontal. And when I resolve 69 in the horizontal, point to this side, and to be 69 cos theta. 69 cos theta should be equal to the tension T. So T is going to be equal to 69 cos theta, which will be 69 cos of 44.1. 69 cos 44.1, and that is 49.55. 49.55 or 49.6 newtons, or it can be 50. Approximately, I can set is 50, although I want to have more than two significant figures, I can say 49.6 newtons. But 50 will be acceptable in this case. Define center of gravity. Define center of gravity. At this point, we now know what center of gravity is. That is the point where all the weight, all the weight, all the weight of the object, all the weight of the object may be considered to act. May be considered to act. That is center of gravity, point where all the weight of the object may be considered to act. A uniform rod AB is attached to a vertical wall at A. The rod is held horizontally by a string attached at end B and to point C, as shown in the figure. So the angle between the rod and string at B is 50 degrees. The rod has length 1.2 meters and weight 8.5 newtons. An object O of mass m is hung from the end at B. The tension T in the string is 30 newtons. Use the resolution of forces to calculate the vertical component of T. So we have to draw a vertical line here for us to be able to visualize T. Using 50 degrees, resolving T to the vertical, that would be T sine of 50. If you use the angle here, which is 40 degrees, you can set T cos of 40 degrees. So the vertical component of T, so that means T in the vertical, I'll call T the Y, is going to be T was T, what was the value of T? The tension T in the string is 30, so this will be 30 cos 40, or it will be 30 sine 50, any of those. So we check this, 30 cos 40, that is 22.9, which is approximately 23 newtons. State the principle of moments. So we know that for equilibrium, for body and rotational equilibrium, the sum of clockwise moments must be equal to the sum of anti-clockwise moments about the same point. So I'll simply say for a body in rotational equilibrium, for body in rotational equilibrium, the sum of clockwise moments about a point equals the sum of anti-clockwise moments about the same point. The sum of clockwise moments about a point is equal to the sum of anti-clockwise moments about the same point. That is the principle of moments. Use the principle of moments and take moments about A to show that the weight of the object O is 19. So we are going to take moments about point A. So this is going to be clockwise, this is going to be clockwise, and the vertical component of T will be actually causing an anti-clockwise moment. So if I take the force here to be W, so the weight W is going times the perpendicular distance, which is 1.2 plus 8.5. Remember, 8.5 was the weight of the beam. That means it is at the midpoint. That is at 0.6. So this distance is 0.6 from A. So 8.5 times 0.6, those are the clockwise moments. Should be equal to anti-clockwise moments, which is caused by the vertical component of the tension, which will be, of course, the horizontal component of T has no moments because it will act through point A. The line goes through point A. In the horizontal, the line will be through point A for T, which is T cos 50. It is T sine 50 which has moments, and its moment is anti-clockwise. So T sine 50 or T cos 40, which we got as 23, times the perpendicular distance, which is 1.2. So those are the moments. So let's say that the weight W times 1.2 plus 8.5 times 0.6. This should give us 23 times 1.2. So we press our calculator, 23 times 1.2. Then we subtract 8.5 times 0.6. And then we divide by 1.2. So that is 18.75, which is approximately 19. So W is equal to 18.75, which is approximately 19 newtons. Determine the mass m of the object. So mass is equal to the weight divided by g. So if the weight is about 18.75 and g is 9.81, so the answer divided by 9.81, so that is 1.9. So this is 1.9. Use the concept of equilibrium to explain why a force must act on the rod at A. Let's go back to A. So the concept of equilibrium requires that the resultant force is zero. Yes, we can say that the 8.5 newtons upwards and the weight downwards is balanced by the component of T in the vertical. But there's a component of T towards the wall, which is going to be T. When I use 50 degrees, it will be T cos 50. It points towards the wall. Therefore, there should be a force from the wall towards the beam to balance the component of T in the horizontal. So the question says use the concept of equilibrium to explain why a force must act on the rod at A. So we say for equilibrium, the resultant force must be zero for equilibrium. For equilibrium, resultant force and moment must be equal to zero. Must be equal to zero for equilibrium. So since the upward force does not equal downward force, so the beam is not going to be balanced by the forces shown there. We notice that the upward force is 23, the downward force is going to be 8.5 plus the weight, which is 1.19. It means that one there, it is already not balanced. Also notice that we have just mentioned that the weight has a component. I mean, the tension T has a component which is towards the wall. Therefore, the wall must be exerting an equal but opposite force to the beam. So if the wall exerts an equal but opposite force to the beam, there must also be a force which is acting vertically downwards, because the tension, the weight downwards is 8.5 plus the weight of the mass, which is 19. It is not equal to 23 upwards, which was the vertical component. So there must be another force. There must be another force, which is most likely going to be this minus 23. So we are saying for equilibrium, the resultant force and moment must be equal to zero. Since the upward force does not equal the downward force, since the upward force does not equal downward force, so the beam is not balanced. The beam is not is not balanced by the forces shown. So there must be another force, which will be, we have 8.5 downwards plus 19 downwards, which gives us 27.5, but the upward force was 23, so minus 23. So there must be another force of 4.5 newtons required to balance. There must be another upward force of 4.5 newtons required to balance the forces. So for equilibrium, the resultant force must be zero, the resultant moment must be zero. Since the upward force does not equal to the downward force, the beam is not balanced by the forces which are shown there. So that means there must be another force acting at the rod. And this one is going to be acting upwards and should be 4.5 to balance the total force downwards. A uniform plank AB of length 5 meters, it is uniform. Its weight must be at the center. So the distance is from the end to the plank. Because it is length 5 meters, this is going to be 2.5 meters. The other one is also going to be 2.5 meters. A man of weight 880 newtons stands a distance x from end A. The ground exerts a vertical force Fa on plank A and a vertical force Fb on B. As the man moves along the plank is always in equilibrium. So if it is always in equilibrium, perhaps the total forces upwards are always equal to the total forces downwards. Explain why the sum of the forces Fa and Fb is constant no matter where the man stands on the plank. So a resultant force is always going to be zero, since the weight of the plank downwards plus the weight of the man downwards is always going to be equal to Fa plus Fb. So the resultant force is always zero. The resultant force will always be zero since the weight of the plank plus the weight of the man is always going to be equal to Fa plus Fb. So it means the resultant force is always going to be zero. Or you could simply say 200 plus 880 is always going to be equal to Fa plus Fb. So wherever the man will be, the sum of the forces downwards will be 200 plus 880, which is going to always be equal to Fa plus Fb. The man stands a distance of 0.5 meters from end A. That is now x is 0.5 meters from end A. Use the principle of moments to calculate the magnitude of Fb. So we can take moments about A. If I take moments about A, Fa has no moment. It is only Fb with a moment, which will be Fb times its perpendicular distance, which will be 5. Then this one will have moment, which is clockwise. 200 will have moments, which is clockwise. Fb will have anti-clockwise moment. So anti-clockwise moment will be Fb times this perpendicular distance 5. This should be equal to, for equilibrium, clockwise moment we have 880, that is for the man, his distance is 0.5 plus 200 times the distance, which is 2.5. That will give us Fb. So we shall simply say Fb. So we are taking moments about A. Since it is 4 marks, we can write something here. So the sum of clockwise moments is going to be equal to the sum of anticlockwise moments. The sum of clockwise moments is going to be equal to the sum of anticlockwise moments, and I'm going to take moments about A. So that we have seen FB times perpendicular distance 5.0 is going to be 880 times the perpendicular distance, which was given as 0.5, plus 200. The perpendicular distance is 2.5. So we check with our calculator. 200 times 2.5 plus 880 times 0.5. Then we divide this by 5. That is 188. So the force FB is 188 newtons. The variation with distance x of force FA is shown in the figure. So we can see the variation. So we are seeing that I think this is the variation of FA. Note that the downward force, we have said that FA plus FB should always be equal to 200 downwards plus 880. In other words, FA plus FB should always be, what is the sum? 200 plus 880, that is 1080. So the sum is always going to be 1080, FA plus FB. So we are seeing that this starts from, okay, this stops at this point here, and I think this is 100. So when FA is 100, what is FB? When FA is 100, FB must be 9. For FA equals to 100, FB will be equal to 1090 minus 100. That one minus 100, 980. And I think 980 is here. When FA is 100, that is at 5 meters, the other one will be 980. And when FA is 980, the other one should be 100. So they want us to, on the axis, sketch a graph to show the variation with x of FB. So it will just be the opposite of that. So I'll draw a graph which starts from 100 up to 980, somewhere there. So that is the graph of FA, I mean FB. So this is FB. A boat travels across a river in which the water is moving at a speed of 1.8 meters per second. The velocity vectors for the boat and the river water are shown in the figure. It is shown to scale. That is very important. It is shown to scale. Okay. In still water, the speed of the boat is 3 meters per second. The boat is directed at an angle of 60 degrees to the river bank. On the figure, draw a vector triangle or a scale diagram to show the resultant velocity of the boat. So since this is drawn to scale, I can just use the scale. So I'll transfer the vector, the water velocity, to the top of the boat velocity. Let me see the length representing the water velocity. Using a ruler, I'm measuring the line of water velocity using my ruler. That is 4.12. So that is 4.2. I'll draw a horizontal line here, which is of 4.2 centimeters. So that is the horizontal velocity of 4. This is 1.8 meters per second. We're joining them head to tail. That means the resultant velocity will be somewhere here. So this will be the resultant. So since it is drawn to scale, we can just find a scale. We can just find a scale and then we use it to find the resultant, or you can calculate because you are using the same triangle. So this angle is going to be 60 degrees. You can use the cosine rule because you have joined the vectors head to tail. But using the scale, let me check the scale. Remember we said it was 4.2 centimeters, which represented 1.8 meters per second from the diagram. I measured 4.2 centimeters and they were representing 1.8 meters per second. That means 1 centimeter was representing 1.8 over 4.2 meters per second. So let's find the resultant now by measuring the length representing the resultant. So this is 6.1. So this is 6.1 centimeters. So R is 6.1 centimeters times the scale, which is 1.8 over 4.2. So 6.1 times 1.8 divided by 4.2, which is approximately 2.6. So this means the resultant is 2.6 meters per second from the scale. Alternatively, we can use the cosine rule since they didn't suggest any method. However, they just told us to use the vector triangle or a scale diagram. For a vector triangle, I can use the cosine rule. So from the cosine rule, r squared is going to be equal to 3 squared plus 1.8 squared minus 2 cos of the product. So we have r squared is equal to 3 squared plus 1.8 squared minus 2 times 3 times 1.8 cos of the angle between them after joining them head to tail, which is cos of 60. So 3 squared plus 1.8 squared minus 2 times 3 times 1.8 cos of 60. Then we find the square root of the answer, which is 2.6. So R is 2.6. A rod PQ is attached at point at P to a vertical wall as shown in the figure. The length of the rod is 1.6 meters. The weight W of the rod acts 0.6 meters from P. The rod is kept horizontal, so it means this distance here is 1.6. We may want it. In horizontal and in equilibrium by a wire attached to Q and to the wall of at R. The wire produces a force F on the rod of 44 newtons at 30 degrees to the horizontal. Determine the vertical component of F. So we resolve this in the vertical. If I use the angle 30, F in the vertical will be F sine of 30, resolving vertically. Resolving by now should be easy. So F in the vertical is going to be 44 because F is 44. So that will be F is 44 sine of 30. Sine of 30 is a half. So that means this will be 22. You can check that. 44 sine of 30, which is 22. Then determine the horizontal component of F. So we are resolving F in the horizontal, which will just be 44 cos of 30. So 44 cos 30, which is 38.1 newtons. By taking moments about P, determine the weight W of the rod. So we're going to take moments about P. W causes clockwise moments, but the vertical component of F causes anti-clockwise moments. So we shall simply say the vertical component, which is F sine 30, that is 22, times the perpendicular distance, which is 1.6, should be equal to W times the perpendicular distance, which is 0.64. This is anti-clockwise, that is clockwise. So we simply say the weight W times its perpendicular distance from P, which is 0.64, should be equal to the other vertical component, which is 22 times 1.60. We take the vertical component because it's the vertical component which has moment about P. The horizontal component has no moment. Its line of action will act through P. So we simplify this with our calculator. 22 times 1.6 divided by 0.64. So that is 55. So W is 55. Explain why the wall must exert a force. Explain why the wall must exert a force on the rod at P. Of course, we see that the vertical component is 22, and we are seeing that the weight is 55, and they are not equal. So that means there must be a force on from the wall, which must be, first of all, balancing the horizontal component and also balancing the giving us a vertical component of force, or a vertical force which which adds with F sine 30 to balance the weight. That means this force must be acting somewhere here in between these two. It must be acting somewhere in between these two forces, the horizontal, which balances the horizontal component of F, and the vertical, which balances with the total forces with the weight downwards. So we are saying F has a horizontal component, F has a horizontal component which is not balanced by W. Which is not balanced by W. So there must be a force on the rod to balance this component. So there must be a force on the rod to balance this component. There must be a force on the rod to balance the horizontal component. That's number one. On the figure, draw an arrow to represent the force acting on the rod at P. Label your arrow with the letter S. So I have said, because first of all, the total vertical force, the vertical force upwards is 20, and that is upwards, and downwards is the weight, which is 55. They are not equal. So it means there is an upward force here, which is going to be around 32 newtons upwards to balance the 55 downwards. That's one. Number two, there is a force in the horizontal, which is the horizontal component that we have seen as 38.1. This must be balanced by another force acting at point P towards the rod in the opposite direction, which should also be 38.1. So these two forces here must be here. This is going to be 32 and this is going to be 38.1. So the resultant of these two forces is actually the force acting at this point P. So they say draw an arrow to represent the force acting on the rod at P. So the arrow will be here. That will be the arrow. So I'll remove all the other arrows which I've used for demonstration, and I'll leave that arrow there because it is the most important one. So the arrow we are looking for is this one here. Sorry. I'll use a ruler to draw it better. It must be between and somewhere here. So that is the arrow we are looking for. Show that the figure shows liquid in a cylindrical container, as shown here. The cross-sectional area of the container is A. The height of the column of the liquid is h, and the density of the liquid is rho. Show that the pressure P due to the liquid on the base of the cylinder is given by that. So pressure is force over area. Which force is going to be the weight divided by the area? And the base area, the weight is going to be mg, of course. So the weight is going to be mg, which mass is density times volume, then times g. The volume is equal to the cross-sectional area times the height h. So it means the pressure is going to be the force, which is density, times the cross-sectional area times h times g, then divide by the area A. So we notice that A cancels, so pressure is equal to density times g times h. The variation with the height h of the total pressure P on the base of the cylinder is shown here. Explain why the line of the graph in the figure does not pass through the origin. We are seeing that at h equals to 0, there is a value which could be accounted for by maybe air pressure or atmospheric pressure. So explain why the line of the graph does not pass through the origin. So when h is 0, when the height is 0, when the depth is 0, the pressure is not 0. The pressure is not 0 due to the pressure from the atmosphere, due to the pressure from the atmosphere. Then use the data in the figure to calculate the density of the liquid in the cylinder. So this is a graph of pressure against H. We know that pressure is equal to H rho times G. So since it is pressure against H, compare with Y is equal to mx plus C, you notice that the gradient is going to be density times G. So gradient is density times G. The gradient is equal to the density times G. But what is the gradient? On the vertical axis, we can start with On the vertical axis, we can have the gradient as, I will take the gradient, let me see, 3. Okay, 3 is fine. And 1.5? Yes. So I'll take the gradient as 3 minus 1. Gradient equals to 3.0 minus 1.0, and this is times 10 power 5. Divide by, on the x-axis, I'll have 1.5 minus 0. So that is 1.5 minus 0. Then the units here were meters, so that is fine. So that is the gradient. Let's check the gradient. 3 minus 1, that is times 1 exponent 5. I just want to bring in the power. Divide by 1.5. So the gradient is that. Okay, let me just find the density by saying density is going to be 2 times 10 power 5 divided by 1.5 in the denominator times 9.81. I'm dividing by g, 9.81. So I will just say that answer divide by 9.81, which is 13,591. 13,591, which is approximately 14,000. That is the density. Okay, so I want to stop here with the part 2, and I will start from this point in part 3. I hope you enjoyed this video. I hope it is helpful. You have learned something from this, and I wish you a blessed day. Bye bye.